All right, good afternoon. And this is the first part of the second week's PA system series, one of two. Okay. How are we going to start this? Okay. So, okay, we're going to do this this way here. Let's say we do have, because I'm going to try to. I talked to the other group, and you haven't got that information yet. So I'm just going to give you some heads up. You will study that again in other subjects, but just so we have some understanding of how things work. This first part of the PA system, PA systems, talks about something that's called the distributed audio, and also it's called constant voltage system. These are the ceiling speakers that you can see in schools and hospitals hallways, in the ceiling tiles, generally made for public announcements, part of the fire and safety regulations and all that stuff. So this is the PA system thing here. So, okay, first thing is that, let's say we have oops. Okay, you didn't see that. It was the weather report started popping up. We don't need that. Okay. Resistors. Let's get a pen here. Get a pen. All right. So when we have a couple of resistors, resistor 1, resistor, what's a ugly resistor, but we know what's going on. R1, R2. And let's use that resistance values that are typical for the speakers or loudspeakers. So this one is going to have 8 ohms, and that one is also going to have 8 ohms, okay? And when we connect our ohm meter between these two terminals, what reading are we going to have? Anybody can type in the chat line, or you can just pipe in on voice. That's fine. But I need some participation here. It's a nice warm afternoon. We don't want to fall asleep. All right, so what are we going to have as a total resistance between this point and that point? Here's 8 and here's 8.
16.
16. There we go. All right, cool. All right. So let's say we have this kind of a scenario here. Here is resistor 1, and here is resistor 2, and we connect them like this, which is a parallel connection. And again, both of them are 8 ohms. What are we going to have between these 2 points now? Just humor me. 4. There we go. Because that's how things work in parallel. The formula is slightly different, and it just so happens that if the values are the same, then we just divide that value by the number of the devices, and we get that. So 8 plus, oh, sorry, not 8. 8 is the value of the resistor. How many of them we have in parallel? 2, so 8 divided by 2, that's going to give us 4. All right. Well, as we know, the amplifier's impedance, and we will talk about exactly what impedance is at later weeks. But impedance is the opposition to current flow, DC and AC included. So the DC type of resistance is called a resistance, And the AC type of resistance is called reactance because reactive elements will have different resistance depending on what frequency goes through them. And usually we will talk about capacitors and coils. And in this case, we're going to talk about coils because speakers do have coils. All right. So the impedance of the amplifier, of the audio amplifier, most of the time, although sometimes, in some specialty cases, you're going to have different, but let's say we have 8 ohms impedance on the output, which is the impedance is basically the reactance and the resistance combined, and impedance does have an angle. So we were talking about the output impedance of the amplifier, and we have a loudspeaker that we're going to connect to that. So we're going to connect that here, and here is the ground reference or the other return path. So we're just going to draw it just like that, and we're going to connect that, and we have 8 ohms of the speaker impedance. Coming out of the amplifier, we have 8 ohms impedance, so the impedances are matched. We need those impedances. If we connect 2 devices together and we transfer power between one and the other, from one to the other, we need to have the impedances matched. Just like the water. I am not the fond of analyzing things by water, so comparing every electrical circuit to water, but in this case, I make an exception, right? Because it's just, it works well that way. Why do we need to match the impedances between the output device of whatever the device is sending the energy or the content with the receiver, which in this case is the loudspeaker, or technically it's our transducer, but it does have a receiving terminal. Okay? The answer is for the purpose of maximum power transfer. Okay? If the impedances are mismatched, then not all the power is going to go from the output of whatever device here to the input of whatever this device is. Some of the power is going to get lost somewhere, and usually it's going to dissipate itself or dissipate as heat. Sometimes it's going to dissipate as heat in one device or the other device or in the wires. Usually it's going to heat up the amplifier. How does that work? Why do we need impedances matched? Well, here's my water example. Here's one pipe, okay? Well, sending water. And we're just going to connect another pipe right to it. So it's just like see-through, okay? And we're going to open the interface. Yeah, it's open. Those pipes are joined and that thing is open. So the water is going to flow as it does. No changes. No changes in pressure. No changes in the speed of the flow or rate of the flow. Things are going to, because those two are matched. Now, when we do, see what's going on over here. When we connect the pipe of one type of diameter and that one, we're going to have another thinner pipe happening connected to it. So when we send water at certain pressure and a certain rate of flow, then in this case, in this spot right here, things are going to get funny. So the pressure is going to be different. The amount of water flow per certain amount of time is going, so things are going to flow different. Yeah. So we're not going to have the maximum power transfer from one to the other. Or if we go the other way, if we have a thin pipe here, and then it's connected to a thicker pipe, and the water is flowing at a certain whatever parameters that we did, Then if we open the valve right here, then we're not going to have the same water flow because that is just going to start accumulating on the bottom and it's going to start filling up the pipe and that's going to just kind of spill out the bottom. So still we're not going to get this. So the same thing with electronic devices. We need to match the impedances. The impedance is the thickness of the pipe, kind of in comparison to that, in order to get maximum power transfer. All right. So let's say we need to connect many speakers. Here's an amplifier somewhere on, sitting somewhere in some sort of office. Here's the amplifier, and it has 8 ohm output. Always write the unit. Okay. And we have a bunch of ceiling speakers. All right. Different sizes. Okay. Now let's say we have, and they just continue, just keep continuing, let's say 50 of those. And they're all 8 ohms. 8 ohms. 8 ohms. I'm not going to write the unit right now, so forgive me. Um, Now, if we connect them in series, then we're going to have a huge common impedance, total impedance for those. We're going to have 8 ohms here, and over there we could have 500 ohms. No good. No maximum power transfer. Let's see what happens if we connect them in parallel. Then we're going to have, out of like 50 speakers, we're going to have pretty much close to a zero, because when we keep adding in parallel, we are providing just one more pathway for the currents to flow, so the total resistance goes down. And it's always going to be less than the smallest resistance of the smallest device. So that's also no good. We're definitely going to burn out the amplifier. It's just like almost like connecting it straight to ground. What can we do? Well, what we could do is, and this is something that is not done, but just follow me with what I'm going to say. When we have the speaker, I'm just going to draw them as resistors, okay? Okay, here's resistor 1, resistor 2, and then we have resistor 3, resistor 4. And if we connect them like this, between these two terminals here, we're going to have 8 plus 8 is going to give us 16, right, total. And that is also going to give us 16 in total because they're all 8 ohms, and those in parallel, that's going to give us 8 ohms on the output. So that's, and we could keep doing that with many speakers, just keep doing that, working out that network and increasing and reducing, increasing this. So out of 50 speakers or 60 speakers, you still can have 8 ohms of total resistance or impedance. Well, let's say you have a school to arm with the speakers, and the school is relatively big. So one hallway is going to have maybe 50 speakers. The other one is going to have 30 speakers. And the other one is going to have 25 speakers. And all of those speakers are going to run from maybe one channel that is looking for 8 ohms. So let's say you have 300 speakers there. And can you do that serious parallel combination to do that? Yes, but it would be extremely impractical. And if there's anything that you need to change, like add one more speaker somewhere there, then the whole thing, you have to do it again. No, that's not how things are being done. So we got something else. Oops. Here, let me just erase this here. Now we have some wonderful device that is called a transformer. A transformer is a bunch of wire wound on the primary winding, and in close proximity, we have secondary winding with the terminals here and the terminals here. Well, by the means of induction, because if we have one wire and it's conducting current, it is going to have a magnetic field spinning around it. And if you put another wire beside that with the close proximity so that that magnetic field is going to affect that, it is going to cause a current flow in the other conductor. However, it only works with AC. What does it mean that it works with AC? The magnetic field has to be changing in order to that induction to happen. So if there is a current here causing the magnetic field strong enough, and you just bring that wire in and out, in and out, in and out, then you're going to cause an AC current. But what's happening if we have AC here? Well, the current flows, climbs up and climbs down, climbs up and climbs down the other way. So it's basically flowing one way and the other, one way and the other. So that magnetic field is changing all the time. It's going one way, growing big, and then it's getting smaller and growing big the other way. So this wire here is exposed to a changing magnetic field. So then the induction can happen. I think I'm going to sneeze. There you go. So if we have the same amount of wounds on the primary and the secondary, we're going to have 1-to-1 ratio. So if we have, let's say, 100 volts on that, we're going to have 100 volts on the other, so primary and the secondary. Those transformers, yes, they're also being used. They're called isolation transformers. But we can do something more with that. Let's say this here, primary has, well, let's say 1,000 wounds, right? And this one here is going to have 500 wounds only. Right? So then we're going to have 2-to-1 ratio. So out of that 100 volts, we're going to have 50 volts. And we still maintain the 2-to-1 ratio. And that can be solved, that can be done till the cows come home. You can have different amounts of windings and you have different ratios, and you're going to accomplish different voltages. Also, if you do the winding, the secondary winding or the primary winding, let's say this one here. If we every so often, once we keep winding, and then we're going to tap out and just bring out a wire. Okay. And we're going to tap out and bring out a wire here somewhere. And over here, well, let's bring our wire here. So we have different terminals here with, at each point, we have different amount of winding accumulated by this point. So we can have different voltages at different terminals. If, let's say this one is the common one, right? And then we're going to have voltage between here. We're going to have a bigger voltage because the ratio between this and that is going to be basically what it will be. Now, so that's how the transformers transform voltage. They transform. Okay. Now, they keep power. So, if this secondary winding is capable of providing 100 watts, and if we consider the RMS values, power equals current times voltage. So let's say we have capability of 100 watts on the primary winding, then the secondary winding is going to give us also 100 watts because the power goes right through. It's not getting transformed. It's getting transferred. Okay. And the transformers are so efficient. There are different ways of assembling them with the metal core to help the magnetic field flow even better. I'm not going to get into that, but they're so efficient in the range of 98%, close to 99%. So we can consider that, for our purposes, pretty much almost 100% efficient. Wonderful devices. Okay. So the transformers keep the power. So if we have that formula here, what happens if we have different amount of windings here? The power here has to be equal to the power here. So if we decrease the voltage on the secondary, we're going to have the current is going to increase in the circuit in order to keep the equal signs between these two. All right. So so also transformers transform current. Now, if we look at this formula, the Ohm's law, I remember as that there. Okay. V equals current times resistance voltage. Now, what can we do here? The resistance, if we want to extract the resistance of that, R equals, we have to divide it by the current in order for that to be here by itself. So that means in order to keep the equal sign, we have to divide the other side by the current. So we're going to have voltage by current. Now, this is the simple formula for resistance, but using the same logic, it works in a very similar way with impedance. But I'm not going to derive a long formula because that's not this class here. What I'm trying to say here is that the impedance, which is kind of similar to resistance, so I'm kind of stretching the truth a little bit here, but you get my drift. It's also because the impedance is marked with the letter Z. In Canada, Z in state Z. All right. So we can have a transformer that transforms voltage, it transforms current, it transforms also the impedance. Very important. And it just keeps the power. All right. How can we use this? Well, in audio, there are such things because, transformers are different types of transformers. Some of them are power transformers outside, big boxes, powering up the neighborhoods with the power service. But also there are certain audio transformers, and some of them are constructed in a way that they are called impedance matching transformers. Since they transform impedance, we can use them as impedance matching. So if you have, like, for example, I'm pretty sure some of you or some of us, or maybe all of us, we have played with the 555 timer. Let's say you can do the circuitry in a 555 timer that is going to give you 1 kilohertz. I always put units in, not always, but try to always, in square brackets. 1 kilohertz wave. And if you connect that to a tiny speaker, are you going to hear something? You have to put your ear to it. Okay. Because this impedance, the output impedance of the 555 timer, is significantly higher than the input impedance of the speaker. So you're not going to get the maximum power transfer, which is going to demonstrate itself as a weak sound. But if you connect an audio transformer, impedance matching transformer between these two, those windings are going to work things out between each other. And we're going to have something that's called impedance matching going on through the impedance matching transformer. And if you do that, then the sound is just going to come alive. It's going to be quite much more louder, if I could say that. All right. So we're using the transformers as the impedance matching devices. Just going to create a new file. So I want to keep this one here. All right. So now, let's say we have an amplifier. And the amplifier is going to have a wire going on, a long wire. But before we connect that wire or the cable with 2 wires, because we don't have to, positive and return path, before that, we're going to connect something that we call the step-up transformer. Boom, 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 boom. Boom, 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 boom. That's big transformer. The secondary winding is much bigger. It's a winding, okay? So it's a step-up transformer. It steps up the impedance. So here we're going to have something like 8 ohms out of the amplifier. I'm going to step up the impedance to not 8 ohms, but maybe 1900 ohms, 2000 ohms, 1500 ohms, 1200 ohms, something in the range of that. So the impedance is going to be here, the low impedance on this side and high impedance on the other side. Now we have something we can work with. Now notice that the voltage, because this is just a wire, and this is just a wire, so at any point here, the voltage between those is going to be the same. So that's why we call that also a constant voltage system. Okay. So now we connect the wire here. We connect the wire here. And here. We connect. Let's see, that's a connection. Another transformer. And that is going to be connected to a speaker. So over here is a step-down transformer, stepping down the impedance, because we have high impedance here, and we have low impedance here. So look, here's 8 ohms, and here's 8 ohms. Why do that? Why can't we just connect that 8 ohms and skip all the transformers? Well, because in this case, if we do that, we can just keep connecting those that way. All right. I'm just going to draw that this is it here. We can just connect that and connect one more. All right. And connect one more speaker state, because this is going to be called a speaker station. It will be a loudspeaker connected to a smaller transformer, but it does the same thing. It steps down the transformers back to 8 ohms. This way, we don't have to worry about the series parallel combination between the speakers of the same impedance, because the transformers are going to work it out between each other. And we could just keep adding until we run out of power. What do I mean by that? Well, remember when I showed you those here, we can have different tappings. Yeah. Well, those transformers here also, we can have different tappings, and we can use whichever tap we want in order to transfer just the amount of current that we want here, or the amount of power. So let's say this amplifier has a capability of, well, let's get kind of like a round number here, 100 watts. That's the capacity of the amplifier. All right. And the transformers on the speakers stations, they have taps and they are labeled. There's going to be at the secondary transformer, secondary winding of the transformer, something like that, there's going to be one permanent connection to the 8 ohms. So that's not touched. But the primary winding of the transformer is going to have different wires sticking out of there, tapped at different point of that thing being wound in the manufacture. And they're going to be labeled 1 watt, or maybe quarter watt, half watt, 1 watt, 1.5 watt, maybe 2 watts, 4 watts, something like that. And they're never going to be labeled exactly. You know, the 1 watt tapping that we consider 1 watt is going to be like maybe 1.25 watts, something like that. Let's say it's a 1 watt tapping. What does that mean? It means that at the full volume, at the full strength of the signal coming out of the amplifier, when we tap that, which is going to connect just one common to the one, and the other one, let's say we're tapping it at 1 watt and connected to the other conductor of the main audio bus. If this is tapped at 1 watt, at the full strength of the signal, full volume, it is going to use 1 watt of power. And it's going to pump the music out with the strength of 1 watt. Okay. So if we have 100 watt capability of the amplifier, and we have a bunch of speakers tapped at 1 watt, how many speakers can we connect until we run out of power? Are you guys still awake? 100 watts capability, and we have a bunch of speakers tapped at 1 watt, which means it's going to use 1 watt at its full power transmitting audio. How many speakers can we connect to that main audio bus? 100. There you go. All right. It's as simple as it gets. Much simpler than trying to figure out the series parallel combination and all that stuff, and something gets changed. You want to add one more speaker? Sure. Add one more speaker. Boom. Just tap it in. Just connect it in parallel. And you see the voltage across all of them is the same because so that's why we call it constant voltage system distributed audio. Now, we in the industry, we have two systems, if I can say that. One is a 70-volt system, and the other one is 25-volt system. Common systems. Which means that with one, the windings are wound in such way that at the full volume, you're going to have, if you put like a sine wave signal, you're going to have 70-volt RMS going there at the full volume if you have a sine wave. And of course, the 25-volt system is going to have 25 volts. Both of them work just fine. It's just they use different currents, but the power transfer is just getting just the same. But the amplifier could have at its back, it could have one common terminal. Then it's going to have some maybe 4 ohms, 8 ohms, maybe 16 ohms, and then it's going to have 25 volts and 70 volts. So if you have a 70-volt system, you're going to output of the amplifier, you're going to, right here, you're going to connect the common, and the other one's going to go to the one that says 70 volts. And then according to the sticker or some sort of explanation written on the transformer, you're going to use whichever color corresponds to that wattage that you want to tap things at. And the transformers will have a sticker on one side that it will explain to you which colors of the wire, which color of the wire is going to correspond to 1 watt at 70-volt system, and which other color you would have to use if you use 1 watt at 25-volt system. We'll show that to you when we are in class. In class, we do have 70-volt systems, so we're going to use that 70-volt explanation on the transformer. Now, when just the trick of the trade, not the trick of the trade, the secret of the trade is that I remember when you have the PA system at school, high schools, elementary schools, and you have those classroom speakers with the push button to enunciate that you want to make a call to the main office. And also there will be hallway speakers, with just speakers in the ceiling. Same things with the transformer, except the classroom station has another circuitry which is connected to the push button in the class. So if you tap all the classroom speakers at 1/4 watt, and if you tap all the hallway speakers at 1 watt, then you're going to have a proper volume or the balance of volumes when an all call is being made. Because in an all call, all the speakers turn on, classroom speakers and all the hallway speakers. So you also will have something that's called a volume control if you need to. And the volume controls come with different power capabilities. And the volume controls are not like it's not like a potentiometer, just like a slider. That's not it. That's not it. The volume control for this type of system is it has the dial, and it has one kind of common terminal, and it has a bunch of steps, and you just click between one and the other, and it just chooses different taps of the transformer. So there's a transformer at the back of that volume control. I'll show you that when we're in class as well. We have those. We're just not going to use them. But if you want to use it through the volume control, then let's say there's one more speaker here and here. So the volume control will have the input, the terminals that are labeled as input, okay? And they also have terminals that are labeled as output. You just connect them, and the output is going again to the speaker station. That's how things are worked out. You can just put that volume control right in line with that. And this way here, you can just adjust the volume on the one particular speaker without affecting anything else. Well, you're changing the impedances, so it's going to affect a little bit, but not enough to be significant. It's just like if I stood on a scale and that scale would show 120 pounds, right? Right. And if I grabbed a pinch of salt in my hand, yes, technically, me with that pinch of salt is going to, of course, in combination is going to weigh a little bit more, but is that going to be noticeable? No. So that's the analogy that I'm using here. Okay, so I'm going to skip that because we already went through that. That's what things look like. Here is the step-up transformer, and here are the step-down transformers connected to the speaker stations. Here's what the back of the amplifier will look like. Well, let me just... All right, can I zoom in here? Yes, I can. You see here, here's the back of the amplifier. Here's the common, and you can connect an 8-ohm speaker or load, 4-ohm or 8 load, 16-ohm load. And this one doesn't even have 25 volts. It just has the 70-volt output. So that main audio bus is going to go one to common and the other one to 70 volts. There you go. You have that main line. Okay. And this is what the transformer looks like on the speaker baffle on the other side. The 8-ohm winding on the transformer is permanently connected to the 8-ohm, so that's not being touched. And you're going to have one common wire and a bunch of different colors of wires. You're going to choose only one of the colors depending on how you want to tap the speaker. Now, paging horns, 70-volt paging horns, it does have a transformer built inside, and it's going to have just like a control that you can use a slotted screwdriver to turn it and choose different tapping. And it's going to be written on the back of the of that thing here. Here's what the volume control looks like. It's just it's a step. There's no smooth action here. That's what the transformer looks like. Okay, so here's the common, and it says black. So don't look at the wires beside the words here. Read the colors. Like, for example, here's the common, and it's, you can probably see it. It says black, but it's kind of covered by the wires. So black is the common. And then if you want, okay, look, here it shows 70-volt line. So if you're using 70-volt line, if you want to tap the speaker at 1 watt, you would use that yellow on this particular transformer. One goes to common, and one goes to yellow. So in the 70-volt system, that speaker, the transformer that's connected to the speaker, is going to grab 1.25 watts at it when the amplifier is turned 100% of the volume, full blast. Okay. And so on. On the other side of the transformer is going to show, oops, where are we here? On the other side of the transformer, on the other side of the moon here, you're going to see 25 volts. And then again, which wattage corresponds to which wire. How are we doing here? Well, we're almost done. So the lab, one of our groups or two of our groups already have done those labs. We're going to disconnect things that are already connected by the previous group, and we're going to connect them from scratch. And we're going to ring those speakers through with the toning device just to make sure that there's no any short anywhere. So it is safe to connect the main line to the amplifier. And we're going to pump some music. So this way, you have an idea how the commercial distributed audio works. It's also called constant voltage system. And it's using transformers to talk to each other, so to speak, work things out as far as the impedances and all that stuff. So we can just connect everything in parallel, just tap in, tap in, tap in, until we run out of power capability based on the tappings that we have used on our speaker stations. And that's how this is done. I will tell you more from the practical side during the lab, which I think is going to be tomorrow. This is class of 2025 summer at Fenchurch College, in case somebody watches this video 10 years from now. All right, that's it, kids, for today. Thank you for your attention. You're beautiful, but not as beautiful as I am. I'll see you when I see you. Thank you.